In this video, I'll look at a coding method for which can be used, which I primarily came up with, discovered when I tried to come up with some method of error detection and correction. So it can be used both for lossless compression as well as for error detection and correction. So basically it was somehow a discovery of a heuristic. See, when trying to compress information, if you're trying to code, if you wish to code, say, a larger piece of a heuristic, which helps is two simple heuristics which always seem to help is, first is try and cut down the information as much as possible, and code the operations you're trying to cut down as a form of this, and let the size of the code increase. Size of the code information should decrease by as much as possible. Size of the code should increase by as little as possible. So that should be your approach each time. So you whittle down the size of the information that needs to be coded, and keep in bearing in mind how much it has been reduced, always fairly accurately, at the same time coding that information by increasing the value of s by as little as possible, this way. So that is a heuristic. Another thing is, then if we wish to code a larger piece of another heuristic which helped is, if we wish to code a larger piece of information as a smaller piece of information, then coding principle is, then apart from the smaller piece of information, from the given smaller piece of information, apart from this amount of information, the missing piece of the larger piece of information must also be, you must be able to also deduce this part, infer it from this itself. So that apart from this part, the missing pieces also it's a sort of, you should be able to infer or deduce it directly from the way it is coded. So this size. So that these two heuristics help. Here is one of those. For instance, if we have a number here, we know the bit positions 0, 1, 2 and so on up to L dash minus 1. And the weights associated with them are 2 power 0, 2 power 1, 2 power 2 and so on up to 2 power L dash minus 1. Right? Now there's no way, if we have to code it this way, there's no way we can use any other value but power. But I thought most likely would have occurred to us, which is, why not just add just the indexes? Yes, it is valid here. So what we do is, initially we have an L dash bit number. So we count the number of ones in it, say n, and what is the sum of all those values, sum of the indexes 1, 2, for which are 1. Say, I'll call it n naught here, and the sum I will call it, say, t naught. So the maximum value we know will come up to L dash into L dash minus 1 by 2. If we know this value, we can infer and deduce what is the sum of all those values which are not 1, because if this minus that should give you the sum of all those values. Now divide the bit portion itself into two parts, and again note the number of ones here, say n1, and the sum of all the values here n0, say t1, right? Again, you know this is nothing but L dash by 2, so you know what is the sum of values of all the zeros for the left part will come, what is the sum of all the values for since you know what this total sum is, you know what is the sum of the values for the, and then, right, this part will come, right? If you know the sum of the values of this part, and the sum of the values of the total length you know there, so if your value of n2 will be similarly there to t2. What will the value of n2 be? It will be nothing but n0 minus n1, and t2 will be nothing but t0 minus t1. So essentially what is happening is, now if we can reduce the 0 there, right? So we are interested only in the one coding the ones sum, no? So what happens is we can continue to do this. We can infer the entire tree. You only have to code the leftmost length of it. So you need not go up to L dash. You can go up to, say, square root of L dash or something like that. The probability that all these sums will match for a given depth, since all the other counterparts can be inferred from it, therefore the probability that it will match will be very, very small, virtually zero only after a certain depth. So you can, from this information, you can recover the entire string, and you can use it as also good for error detection and correction as well. So it compresses as well as it's a good method for both compression as well as for error detection and correction. For both compression as well as. So here you have n0 comma t0. Initially from this, you can, the 0 part also you can similarly deduce from this. You can deduce the entire tree. So what you here you have n1 comma t1 for only n2 comma t2, n3 comma t3, n4 comma t4, n5 comma t5, n6 comma t6, right? So here we saw similarly you have n3 equal to, if you know what n2 n1 is and n2 is, and you code only this one, you only have to code the left part. You will have a linear code. All here you have n4 will be equal to n1 minus n3, t4 will be equal to t1 minus t3 and so on, right? So then this sum of this minus sum of all of this, this minus sum of all of this will give you this. Then if you know this, then you can calculate this, like this you can keep, just by using these differences. The entire tree can be inferred or deduced just by coding one left part of it. So this method is a simple method which is very effective. The amount of information that you can code will be very large, but the amount of space required to code that will be very, very small.